thanks very much for the invitation and the possibility even to speak online here. So I hope you can hear me. Is it okay? Can you hear me?
Perfect. Yeah.
Perfect. Good. Okay. So congratulations to Michelle. So when I was thinking about what I should talk about here, I was thinking about when I met Michelle first time, and I actually don't remember. But I remember that I met him at some point in Oberwolfach, where I was still a student. I was thinking about triangulated categories at that time, and was going to talks, and I didn't follow many of the talks. And in particular, I didn't know what the Chow group is. And so Michelle explained me what Chow groups are in a very nice and very pleasant way. So I thought I come back to this and give a talk on something around triangulated categories and Chow groups today. So the motivation is certain convolution algebras which come up naturally in representation theory, and I want to put it into a framework of motivic stuff. So, and I want to start with some motivation coming from what I want to call reconstruction problems. I don't know if this is the right name, so maybe I should put it in quotation mark. This is just for this talk. So first, reconstruction problem is if I have A in a abelian category, and I have an object in A, the question is, can I realize A as modules over the endomorphism algebra of this object? And so in particular, is the functor homing from M into this category? Is this an equivalence? And of course, we know that this works sometimes. So for instance, if I have finiteness conditions like having small coproducts and M is a compact projective generator, then we have this standard equivalence, which we always use. And so we can reconstruct somehow the category A from the object M. So let me give a different example. So if C is an idempotent complete triangulated category, and I have a family of objects, T, a family of objects in this triangulated category, then I can ask the question, when I hom from this family, so I take the direct sum of all objects in T and I hom into my category, does it give me some kind of equivalence? And so we know when I take what is generated by T under isomorphism, direct sums and direct summands, then this is equivalent to modules, say finitely generated projective modules over the endomorphism ring of this T. And so by endomorphism ring, I mean this locally finite version of it. I take homs between any object, say M and N, where M and N is in T. So this is locally finite endomorphism. So that's a nice example of such a reconstruction. The third example I want to give is one which comes really, for me, often in representation theory. So if I take a Koszul algebra, or let's say first a positively graded algebra, so which is more precisely a non-negatively graded algebra, A, and I assume that A0 is semi-simple, so it's a direct sum of simple objects. So they are simple. So I want to assume that this is a Koszul algebra. So then it's in particular quadratic, and I can build the quadratic dual A3, which is by definition, if you want, the X algebra from this A0 to A0 over A. And I want to ask the question, can I reconstruct my original derived category from A? And this is exactly what Koszul duality does. So I can take, say, the bounded derived category or some other finiteness condition, which I don't want to specify here. I take graded A modules. And I can look at graded A3 modules. And I have a corresponding equivalence of graded categories, which sends, when I take for T, the family of objects given by these simples, shifted in any degree. So this is the internal shift and the homological shift. So it's internal and this is homological. Then I have this family T in here, and I can look what is generated by this under isomorphism and in the triangulated sense. And this is then exactly equivalent to perfect complexes on the other side. So that means this is again a way to reconstruct the original category, or the A-Schrick category, from a collection of objects. So this is this equivalence then causal duality. And let me do a last example. So let's say A is the highest weight category. So we have the Moore structure of standard objects. And the projectives are filtered by standard objects. And I take T, an isomorphism classes of certain objects. So in the highest weight category, I have standard objects and I have dual standard objects. And I can ask the question, what are the objects which have both a standard and a dual standard filtration? And these are so-called tilting objects. So I have isomorphism classes of tilting objects. So these in particular have the condition or the property that they have no self-X. And so I can take E as being the endomorphisming of all these indecomposable tilting objects. And then I can look at what is generated by this family of objects under isomorphism and taking triangles in the corresponding triangulated category, and I get an equivalence of categories to perfect complexes in E, where E is this endomorphism ring of T, defined as above, this local finite endomorphism ring. And so modules over E, locally finite dimensional modules over E, this is the Ringel dual category. So I can construct somehow the original category by passing to the Ringel dual or recover the original category. So, but the warning is, in general, modules over the endomorphism ring of T, in some sense, doesn't recover the category or reconstruct the category. So without passing to A infinity structures. So there's this, for instance, this nice paper of Bernhard Keller, who describes nicely that if you take a collection of objects generating a triangulated category or derived category, then you can recover the original category by modules over this endomorphism ring if you allow passing to it A infinity structures. And so, for instance, in highest weight categories, if I would take not tilting objects but standard objects, then one has really to take a non-trivial A infinity structure. So, and now my motivation for this talk is I would like to have a setup where we have formality. So that means that we can recover our triangulated category from endomorphism of a tilting object or some kind of nice generating object without having to pass to affinity structures. And I want to connect this with examples coming from representation theory. So what does representation theory do for us? So geometric representation theory provides examples. So for instance, of causal algebras. And so in this case, we have this nice equivalence, which I mentioned above. Also with algebras where the grading comes from some kind of homological gradings or geometric gradings using perverse sheaves or demodules. So this is origin is homological or geometric. And often these algebras A's are direct sum of X algebras of certain objects, Li, Lj, I sum over I and J. And these are simple objects and often perverse sheaves or something like this. So this is often realized like this. So that means the question is now, can we say something about reconstruction of our categories, like a derived category around perverse sheaves from modules over this algebra? And so there's formality results in the literature, for instance, by people like Ryder or Schnürer, McNamara, or Betzokavnikov, many people, which is usually hard work when you do it case by case, depending on your algebra A. So now I want to set up a general philosophy which connects these kind of algebras with Chow groups and motifs, which gives an analog for these formality theorems. So now let me start with the real talk. So the setup is we have varieties which are defined over finite field, FP with the algebraic closure. And I look at coefficients of cohomology and sheaves in rational numbers. So and then the setup is I want to have xi, that's a variety, not necessarily, xi is smooth varieties, where I is from some labeling set I, and it sits over another variety n. And I have pi, a proper map. And this map can be also Chi equivariant, if you want, for Chi, say, an affine algebra. So, and what we can do from this, and this is often applied in geometric representation theory, we can build an algebra E, which is a convolution algebra. And it comes from, I take the following thing, I take the Chow groups of the fiber products of this xi with xj over n. So I have my xi and xj upstairs, and I can take it over n, this fiber product, and the corresponding Chow group. And if I want, I can also take it equivariantly. And so this is the equivariant extension. And so I call this a motific convolution algebra, because it's first a vector space over Q, but it becomes an algebra via convolution. So let me recall you what convolution is. So here is the setup. I have these varieties, xi's over n. So downstairs is n. And then if I have a product, a fiber product, xi with xj and xj with xk, then I can take the product. I have the corresponding projection maps, and also have the projection to xi times xk. So, and I can take two cycles in my Chow ring, one from this fiber product and one from this fiber product. I view it as something in the Chow ring of the product. I pull it back along the diagonal to this double fiber product, and then I push it forward via the projection to xi times xk. So, and this here's the formula. So the convolution product is pulling back, pushing forward, and denoted by I star beta. And so this turns these direct sums of all these Chow rings into an algebra, which I want to call this convolution algebra. And so this defines then for me this guy here. And that's a nice associative algebra. And on the other hand, I want to realize it. So if I think in terms of algebras which come up in geometric representation theory, I want to compare it with something which I want to call, so let's say this is E convolution for convolution product, and I want to call a different algebra E for mod. This is standing for motifs, and it should be constructed in the following way. It should be like an X algebra. So I take HOMS from the following thing. I take the constant sheaf on xi and push it forward via my map to n. And then I take the constant sheaf on xj and I push it forward via my map n. And I want to take HOMS between them up to some shifts and some grading. So, but the question is, in which kind of category do I want to do it? Oops. So that means that what I want to ask is there a good category where, first of all, this shift makes sense? And secondly, where I can take these HOMs so that there's a relationship between this thing and that thing. And traditionally, one would work here in some kind of category of perverse sheaves with some Hodge filtration or some kind of D modules with some Hodge filtration. But I find this pretty technical to define this grading using these Hodge filtrations, which then corresponds to this grading here. So I would like to suggest some other setup which is motivated by this motifs, which is indicated here in this subset, in this subscript. So what I want to have is I want to construct a category which is now just this green-blue box, this green little box, such that when I take a certain subcategory similar to the ones I defined before, so it's a subcategory generated by this collection of objects which come from this push forward of these constant shifts, and I close it under isomorphisms, direct sums, direct summons, and triangles, then this should live inside this sort of natural category. So the goal of the talk is to explain a little bit what this category is and where this grading shift comes from naturally, and then state a formality theorem. So let me state the theorem, assuming these green boxes, which I want to see as black boxes, where we don't know yet in which category we are. So the theorem is, and I should say this is joint work with Jens Eberhard. So I assume two properties. One is a pure tate property, and the other one is a sort of finite orbits property. So this pure tate is a serious assumption, which we really need, and this finite orbits is something which is, I think, stronger than one needs, but helpful for proofs. So what is this finite orbit properties? I take my map here, and I want to apply it to xi, and sits inside n, and it should have finitely many g elements. So on this pure tate condition, I stated a bit vaguely at the moment, for all little x in my n, I want that if I take the fiber of this, oh, sorry, I denoted it now mu. I'm always changing notation. Sorry, I should denote this mu. If I take the fiber of this, then it should be pure tate. So I want to have some cohomology vanishing condition. So I will make this precise in a bit later. But at the moment, let me just say I want to have some kind of cohomology vanishing condition. And then the statement is, when I look at this subcategory here, which I call Springer sheaves or Springer motifs, then this subcategory, G equivariantly, is equivalent to the derived category of, to the perfect complexes in the category of graded modules over this algebra E, where this algebra E is this convolution algebra, which I defined before. So on the main point here is that I had taken just perfect complexes over this algebra, no higher A infinity structure or whatever. And on the other hand, I have what is generated by these objects here in an ambient triangulated category. And so this ambient triangulated category, so this is what I want to take at the moment as a black box. I want to call it as derived M. M stands for motifs. So this is the equivariant, the derived category or triangulated category of equivariant motivic sheaves on M. So this definition is Tutu-Voevodsky. That's a nice triangulated category, which has a six-functor formalism, etc. But it's pretty hard to construct or define this category. So at the moment, this is my black box. And so this is what I denoted by this green upstairs. And so the statement is, when I embed this into this unknown at the moment category, then I have a formality theorem for free without using any higher A infinity structure. And then the second statement is, under these assumptions, is that this convolution algebra is equivalent to this motivic algebra, which I defined here, which is taking homes of these objects, these pushed forward analogs of constant sheaves, but in this category of motifs. And this is an isomorphism of graded algebras, where on the left-hand side, on this convolution product, I have the internal grading shift, which you just get from the cohomology grading here. And on the other side, I have this shift, which is a derived shift by 2. That's just a normalization problem. If you don't like it, you can just write 1. And this is some sort of Tate shift, which is built into this categories of equivariant motivic sheaves. So that's the theorem. And now what I want to do now is I want to explain a little bit why this theorem makes sense and give some kind of intuition what this equivariant motivic sheaves category is supposed to be. And so the main tool behind the theorem, which we use, is the following proposition. So under the assumption, this PT and PO, this family of objects, which is the family of objects of the form this mu I pushed forward Q or Xi is a tilting family. So this is very similar to the examples which we had before, where these equivalences worked, where we could reconstruct the category. So by definition, this means that Homs from M to N shifted by something is 0, where the shift is non-zero for any M and N inside my family of objects. So, and I call this TSPR, and this stands for Springer, because I mimic a construction which comes from Springer theory. So now, after this sort of abstract nonsense, I want to give some examples of algebras which really appear in this way. So this was the product. So here is some examples. So the first example I want to give is the thing which gives the name for the Springer motifs. So this is a Springer resolution. So what I can take is I take a semi-simple Lie algebra, like SLN, for instance. I take nilpotent element in this Lie algebra, this is my N. And then I can resolve this via the Springer resolution. So in SL2, I would have here a double cone of nilpotent elements. And over that, I just have somehow the Kleinian singularity resolution, which you all know. So, and then in this case, I can construct this convolution algebra. And in degree 0, for instance, I get the degree 0 part of this fiber product, homology of this Chow ring of this fiber product. And I can reconstruct the group algebra of the Y group. So, and in general, I get some interesting degenerate affine Hecke algebra via this construction. So that's the basic example. In this case, I only have one variety sitting over this N, so one resolution. But I can also do things like the following. I take a quiver, Q with vertices and arrows, and I can look at representations of this quiver. So this is the set of representations, or the variety of representations with a fixed dimension vector D. And then I can put extra structure, which I call flagged representations, or some people call this quiver flag varieties. So that means I take a representation together with a filtration so that the associated gradient is semi-simple. And so the filtration type is some flag type. So this gives me the filtration. And fixing this a certain flag type gives me a corresponding, maybe I should write this, not D, I should write this mu for the flag type gives me a variety sitting over this representation. So I can forget the filtration, get a representation, and so I have this variety Q depending on the type of filtration sitting over representations. And everything is equivariant with respect to the group, which just changes the coordinates at each vertex of the representation. And so I can plug this into my setting. I have this sort of Fiver-Bodak construction of quiver flag variety over representations with another, where I can take another type. No, I used it D, so let me use D here as well. So I have this Fiver-Bodak. I take the Chow room and take the direct sum of all possible flag types or flag types which I allow, and this gives my convolution algebra. And so this algebra is very famous now. So if I take just flag types which are full flags, so I have a filtration where each subquotient is just a one-dimensional representation, then I get what people call Kähler or Hovanov-Lauda-Rouquier algebras or quiver-Hecke algebras. So these were introduced by Varagnolo-Vassereau in this geometric framework and in algebraic framework by Hovanov-Lauda and independently Rouquier. And if I vary this flag type and allow partial flags, then I get what people call quiver-Chow algebra. And this was introduced by Webster and myself. So that's another important example which fits into this framework. And let me give you two more examples. So for instance, we can take for X the flag variety G mod B for any reductive algebraic group G with Borel B. And I can take the Schubert cell inside any Schubert cell inside this flag variety. So it has a corresponding Schubert variety as a closure. So this W is the labeling set, which is for me an element in the Y group. And now we can ask the question, how can we resolve this corresponding Schubert varieties? So they're in general singular. And so there's the famous Bot-Samuelson resolution, which depends on a reduced expression of this element in the Y group. So this is a nice iterated P1 bundle sitting over this Schubert variety. So I have a map going to my flag variety G mod B, and it's equivariant with respect to the torus. And I can do again this same construction, this convolution product, where I sum over all these Fiver-Bodaks for this different Bot-Samuelson resolution, where I fix for each W a reduced expression. And so this algebra is again a very important algebra coming up in representation theory. So this is what people sometimes call an endomorphism algebra of Sergel bimodules. So because Sergel somehow gave an algebraic description of this algebra in terms of co-invariant rings and invariant rings over polynomials. So these are important algebras. And again, they get a grading by the cohomology grading of these Chow rings. And so I could continue forever in this list. So all these Hecke algebras, graded Hecke algebras, etc., come from this framework. Also, more difficult things like this Coulomb branches algebras, etc. But let me stop here. So these are a few examples. So now we have these examples, and I want to go back to my theorem, which is formulated in the Wake statement. So now my theorem says now I have these algebras here, these convolution algebras, and I want to look at perfect complexes, graded perfect complexes over this algebra E. And I want to connect it with these Springer motifs, which are sitting inside these equivariant motivic sheaves. And I said the main tool which we use to set up this equivalence is that these guys form a tilting family. And actually, what is even more important is that we use weight structures and weight complex functors applying to such a tilting family, which gives then this isomorphism or this equivalence. So now what I want to do now is I want to explain what these weight structures are and how these tilting complexes come in and how we can construct this equivalence. And at the end, I will then roughly say what these motifs are. Okay, so weight structures. So we all know triangulated categories. So here on the right-hand side of this slide, you can see the definition of the triangulated category following BBD. So we have a triangulated category with a T structure following BBD. So I have a triangulated category and a T structure is given by a collection of two full subcategories, T smaller equals 0, T bigger equals 0 with the standard conditions. So now a weight structure is the following, and I follow here Bondarco. Some people also call this co-T structure. But I want to follow the notions of Bondarco. So it's the same thing. We want to have additionally that the categories are idempotent complete to avoid some sort of technical problems. And then it's the same sort of thing. We have two full subcategories called smaller equals 0 and bigger equals 0. But now the conditions somehow for this weight structure are in some sense dual to the condition of a T structure. So for instance, in a T structure, I want to have extensions where A on the left is in T smaller equals 0 and B is in T bigger equal 1. In this side, I have the A is in W bigger equal 1 and the B is in W smaller equals 0. So it's somehow dual, and similarly for the other statement. So this is the definition of a weight structure, and one can give easy examples of such weight structures. So here's an example which I want to call the stupid filtration weight structure. And so you just take, say, A is an idempotent complete category, and I want to assume it's additive. And then I can look at the bounded derived at the bounded category of complexes in A, and I can define a weight structure. So I have to define what is this W greater or equal 0. This is just stupidly taking all complexes X such that Xi is 0 for all I smaller than 0, and I close it under isomorphisms. And the same thing is for smaller or equal 0. So I just take all complexes X such that Xi is 0 for all I bigger than 0, and I close it under isomorphisms. And then the intersection, of course, of these two guys, which is called the heart, is just A itself. And so in contrast to triangulated categories with a T structure, where the heart is an abelian category, this is just an additive category. When I start with an additive category, so it doesn't need to be abelian. That's the first example, and the second example I want to mention is if A is an abelian category, then I want to assume that the projective dimension is finite. Then I can realize the bounded derived category with the category of complexes of projectives up to homotopy. And then the heart, in this case, following the same construction as in the first example, is just the category of projective modules in A. So again, it's only an additive category, and it's not. Okay. So why do I want to talk about these weight structures? So the point is, it's a big. So I was mentioning these categories of motives following Woiwodsky. So it's a big open problem whether this category, which is a triangulated category, has a T structure. I think this is maybe a hopeless problem. But the idea is that this definition of Bondarco, this weight structure, is the correct notion or analog of T structure, which can be applied in this motivic world. And so he actually proved that this exists. And so let me say a little bit about Bondarco's construction. So here's the general construction of Bondarco. How can we define many weight structures from abstract nonsense? So and then he will apply this to this motivic category. So the general construction is when I have my triangulated category, idempotent complete as before, and I want to take a collection of objects. So it's a similar setting as I had before. Then one can take this data and construct a weight structure with the heart. So this is the heart here. So this is everything which is of weight 0 is exactly the category generated by this collection of objects under isomorphism, direct sums and direct summands. And so, for instance, we can think of this example before, where we had these projective modules inside a abelian category A. This is supposed to be this piece here, and we want to realize it as the heart of a weight structure. And so the setup is when T is negative, so that means it has no HOMs in the positive direction, and it generates as a triangulated category my C, then there is such a weight structure. So this in particular can be applied to this example which we had, where we plug in for X and Y these projective objects. So, and this is the general construction, and having such a weight structure, Bondarco constructed a weight complex functor. So what is this weight complex functor? This weight complex functor is dual to a construction which is well known on the level of T structures. So when I have a category C with a triangulated with a T structure, I can take the heart of this T structure. So this is the heart. I can take the bounded derived category and have a functor, which is Beilinson realization functor going to C. So in general, it's not an equivalence, but I have at least a functor. And so following this idea that these weight structures are dual, I'm supposed to having a functor in the opposite direction. And this is what Bondarco constructs. He constructs a weight complex functor starting from my original category C with target the category of so KB of this corresponding heart of the weight structure. So in the example which we had before, the target would be the homotopy category of projective objects in my original category. So the assumption one needs here, and this was pretty surprising for me, so the construction really requires higher structure. Also the formulation doesn't, but I need the assumption that some boundedness conditions or this bounded weight structure, and I have to I need the assumption that my category is realized as a homotopy category of infinity, of some infinity category. So in practice, this is not an assumption for me really, because everything I know is of this form, but one needs it seriously for the construction of the complex. Okay, so now that means we have such a functor, and then the connection with this tilting before is the following. So assuming these assumptions so that we have this functor, one can ask the question, in which cases is this weight complex functor an equivalence? And here's a small proposition which we prove. This is an equivalence if and only if this heart is tilting. So it has no, and tilting means it has no no extensions in either direction, which is non-zero. So that means HOMS from M to N shifted by I is 0 for all I not equal to 0, and M and N in my heart of the weight structure. So whenever I have such a condition, such a tilting family, I have this guy, and they should generate the category, of course. Okay, and so what do I do now with this? So that the philosophy is this Springer motives, which I defined before. So this push forwards of this somehow constant sheaves, they form a certain tilting family. Such guys inside this big category of Wolwatsky. And so now let me say something about this category of motives. So are there any questions?
No one is raising their hand, so I think everyone is happy. So yeah, you can continue.
Good. So now, so we have now this abstract nonsense of this weight complex functors, and now I want to connect it on the one hand side with my convolution algebras, which I defined before, and on the other side with this abstract Voivodsky category of motives. And so for me, the idea is the following. So let me first say a little bit vague of the main goal of this slide here. So I start with what I want to call Chow motives. So this comes from a category of correspondences. I have a category of correspondences. Then I do some sort of pretty standard construction for it, which is not very difficult. So I will explain it in a second. I get more or less this Karoubi enclosure of these Chow motives. And then the big point is then Bondarco proved that these Chow motives, and also in the G equivariant version, form the heart of a weight structure on a triangulated category. And this is this derived category of G equivariant geometric motives, or these motivic sheaves of Voivodsky. So that means the way how I see it, there is this complicated category of derived or geometric motives, which is hard to understand. But inside there is it has a weight structure. That's Bondarco's main result. And the heart of this is something which I want to explain in explicit terms. And so at least we understand somehow the analog of projective objects in our previous example in this setup of this derived category of geometric motives. So now let me now start and try to explain what this heart is. Okay, so we have our setup from before. We have our variety n, and we have we had this xi sitting over n, and we turn this data now into a category. Okay, and so what is this category? So the category is the category of correspondences over n, and it has objects which I denote by m, x, n. So this is just a formal notation. So this m stands for motive and x over n. So this is just the formal notation for I have x, a variety sitting over n, and x is supposed to be smooth. And the map is supposed to be proper. So this is my object. So objects are just smooth varieties sitting over m via a proper map. And now what are the morphisms? Morphisms in this category of correspondences is just by definition. So I want to have a morphism space from x over n to y over n. And it's just by definition, these Chow groups of x fiber product over n with y. So that means it's exactly the thing which we defined, or which we took before to define our convolution algebras. And so we can also take everything G equivariantly. So if this is G equivariant, then I have here my G equivariant version, and this is G equivariant, and this is G equivariant. So, okay, so this is for me, a pretty concrete category, and it's additive because we have the disjoint union of varieties. And then I can just take abstractly the Karoubi enclosure of this category. So that's for me an abstract notion, or an abstract thing. So for instance, when I look back, if I take P1 over n, or if you want T star P1 over n, so this was an example which came up before in the Springer resolution. And in the Springer resolution, we know that the degree 0 part of this corresponding convolution algebra, this one here, in degree 0 was this group algebra of the symmetric group S2. And so it has two idempotents. And so this means that this motive in this Karoubi closure decomposes into a direct sum of two things. So one is somehow the analog of the constant sheaf, and the other one is what people call in this motivic world the Lefschetz motive. And so the definition of this Lefschetz motive in general is complicated, but in this case it's just somehow decomposition of this motive corresponding to these two strata in P1. And then formally one takes this Karoubi enclosure of this category of correspondences, one inverts formally powers of these Lefschetz motives, and this is the category of Chow motives, or G equivariant Chow motives. And then there's Bondarkov's big theorem that this is the heart of a weight structure of this derived category of G equivariant geometric motives of Voivodsky. So that means we have a very concrete description of this heart. And so now, the main point of our formality theorem is that inside this big category of motifs, where we understand the heart, and we have a weight structure, these Springer motifs, which I introduced before, form a certain tilting family. And then the theorem is the one which I studied before. So now the assumption can be made precise. So we have this fiber over x for any point x in N, and then the motif corresponding to this has to be pure tate. So that means it has it's of the form, it just looks like this constant motif shifted in the correct degrees. Okay, and the good thing in this category of motifs, I have a shift, a tate shift, which gives me a grading, and this grading really corresponds to the grading on my convolution algebra by under this isomorphism, which where on the left hand side I have homomorphisms in this category here, and on the right hand side I have this. On the right hand side I have homomorphisms in here. And on the left-hand side, I have this convolution. Okay, and what is examples of it? So examples of this equivalence or applications is, yeah, and this maybe I should have said this. So this equivalence is exactly Bondarko's weight complex functor. So an applications is the following. So going back to the previous examples, this Koszul duality fits into this framework. So Koszul duality appears as a weight complex functor. And also these assumptions, PT and FO hold in all the previous examples. And for the Springer fibers in type E, it's not completely trivial that this thing holds. This uses an old paper of De Concini and Procesi. But it holds, assuming for this quiver flag varieties type ADE or A tilde for quiver flag varieties. So in general, we cannot prove this yet, although I believe that it should be true in general. So and what is the advantage of this theorem in relation to known theorems in the literature? So for me, this theorem is pretty appealing in the following way. So I can avoid working with gradings coming from perverse sheaves and D modules, because this grading comes very natural in this category. So the drawback is I have this big black box of this category. But on the other hand, this weight, this heart of this weight structure is very concrete, and it directly connects with this convolution algebra structure on here. And the second example, the second thing why I think this is a good framework is on this category. This is built so that we can somehow change the corresponding fields, although it's technically complicated. But so I expect that one can somehow prove theorems in positive characteristic, which were so far pretty difficult. So and in particular, one has now a framework where we can embed this category of perfect complexes of graded E modules without any higher structure into something which is a nice ambient derived category or triangulated category. Yeah, so I just want to make a little bit of advertisement for these motifs, and I think one should consider them in more in web stations. And I think I stop here. Thanks.
Thank you.